Okay, time for the grand finale. We're going to get back to one of the New Horizons Breakthrough Prize winners and get back to physics and get up into the sky again for some fabulous astrophysics to finish off the afternoon. Our speaker is going to be Samaya Nissanke, who is an astrophysicist at the Grappa Institute, a center for excellence in gravitation and astroparticle physics at the University of Amsterdam. And she just flew in just for this purpose. I think what we're going to hear today is some really exciting new developments in what's called multi-messenger astronomy, which is essentially astronomy based on different methods of detection than we're accustomed to. I think all of us have looked up into the night sky and looked at the stars, and astronomers for many centuries have been using electromagnetic radiation to detect what's up there and learn about how the universe is structured. But what we're going to hear about today are new methods of not using electromagnetic radiation, but other emissions from distant objects, such as, for example, gravitational waves that we heard about earlier. And also, there are a variety of other interesting emissions that some of those objects are producing and that we're learning to detect so that we can see the sky in different ways. And so, as I said, gravitational waves are the main body of work in this area, and in fact our speaker today was a part of the LIGO team that detected those gravitational waves a couple of years ago and actually won a previous breakthrough prize for that collaboration. Okay, so the title of the talk today is New Perspectives into the Universe in the Coming Era of Multi-Messenger Astronomy.
Good afternoon, everyone. I hope you can hear me. So in the spirit of the symposium about the future, I'm absolutely delighted to be here to talk about this rapidly exploding and observationally driven new field of multi-messenger astronomy. And so by multi-messenger, what I'm talking about is radiation that comes from the entire electromagnetic spectrum, as well as gravitational wave spectrum and high-energy particles. Okay, and all the measurements that we're learning from using all these different messengers are allowing us to really make this transformative step forward in having a new perspective in the universe, and in particular in strong field gravity astrophysics. So for the first time, we are actually able to hear through gravitational waves, as well as see through traditional light, the extreme gravity and dynamic universe, as I'll discuss. So 100 years after Einstein's theory of general relativity predicted both gravitational waves and black holes, in 2015, we observed both directly for the first time through the measurement of a pair of black holes merging due to the emission of gravitational waves, essentially taking energy away from the system. And this event occurred 1.3 billion light years away. And the two black holes comprised masses of 29 and 35 times that of the sun. And indeed, the actual duration of the signal lasted only 0.2 seconds. That we actually observed. Okay, and within that 0.2 seconds, we actually observed 3 solar masses of energy that were released within this event. So this made this the most luminous event that we've ever observed in the universe. So essentially, the luminosity was about 100 billion trillion times that of the solar luminosity, as well as 50 times as if you sum up all the light from all the galaxies in the visible universe. So I really think, that was absolutely phenomenal. And the event was detected by the laser interferometric gravitational wave observatories located in Louisiana and Washington State. And in gravitational waves, our measurable is this dimensionless gravitational wave strain, which essentially comprises the amplitude and the phase of these ripples in space-time curvature. Okay, so that is essentially what we're measuring. And the gravitational wave strain has a 1 over distance to the source dependence. And essentially, gravitational waves are coherent, and hence the analogy to sound. Okay, so this is why we say that through gravitational waves, we're actually able to listen to the universe. And so far, within the first 2 years of the operation of the LIGO and Virgo detectors, we have announced at least 10 binary black hole mergers. Moreover, on August the 17th, 2017, over 2 years ago, we observed for the first time a pair of neutron stars actually merging 130 million light years away, both in gravitational waves, so you can see the in-spiral in this movie, as well as in electromagnetic radiation in every part of the electromagnetic spectrum. Okay, so as the movie illustrates, the electromagnetic radiation occurred as a result of the fact that there was during this complicated merger, there was essentially gravitationally unbound material that was flung out. And broadly speaking, we observed these two types of matter outflows. One coming from a jet that was moving essentially close to the speed of light, and the second outflow was more spherical, and initially there was this neutron-rich material that then adiabatically expanded and was then powered subsequently by rapid neutron capture nucleosynthesis, and had long been hypothesized that neutron star binary mergers may indeed be one of the astrophysical sites of the heavy elements. And so this event actually represented a multitude of discoveries that I'm going to focus on in the rest of my talk. And really just to stress that the game-changing sort of aspect of this discovery was actually that we were able, for the first time, to actually pinpoint where the host galaxy and where the event actually happened in the sky by measuring the electromagnetic radiation. And so indeed, the observation of gravitational waves as gamma rays, as well as gamma rays from the signal, initiated this absolutely beautiful and unprecedented campaign of data sets that involved 70 groups over 90 telescopes, both on the ground as well as on space, and over 100 instruments that actually detected the emission in every part of the spectrum. So the optical was detected 11 hours after the event, the infrared at 12 hours, near-infrared at 12 hours, the ultraviolet by the Swift telescope at 15 hours, the X-ray at 9 days, and the radio at 16 days. So this really made this the most studied and a transient event that we've ever observed in the universe. I mean, really just absolutely spectacular. And just to mention that actually this multi-messenger discovery of this event included about over 3,000, apologies because I have a bit of a cold, over 3,000 co-authors actually involved in the multi-messenger discovery, really exemplifying, I think, the global and international efforts of these diverse communities actually coming together and being involved in this discovery. So why are we interested in black holes and neutron stars? Well, black holes represent the extremes of space-time curvature. As we heard today, they essentially have no surface, just an event horizon, which is essentially separating the information from within the black hole's interior with the outside universe. And they're, in some sense, the most simple fundamental objects that we have in the universe. They're entirely described by two numbers, their mass and their spin. Neutron stars, on the other hand, represent both the extremes of space-time as well as dense matter. And so, similar to stellar mass black holes, they actually represent the end states of the lives of massive stars. And their masses essentially range from 1 to a few solar masses, which are crammed into objects with essentially radii of 10 to 15 kilometers, so essentially the size of cities, making their densities as high as if you actually cram the entire of humanity into a sugar cube. Okay, so these really are the most sort of fantastic cosmic laboratories, and indeed the actual mergers of neutron stars make them in some sense, ideal astrophysical colliders. And so, of course, the huge excitement about this field is that from gravitational waves, we're actually able to extract and learn about the source's fundamental properties, such as the black hole masses, the spins, as well as the neutron star equation of state. And from the electromagnetic radiation, we can not only pinpoint where the event happens, but actually say something about the event's energetics, as well as the environment. And so it's really this piecing together of the different pieces of the jigsaw puzzle that allows us to understand compact object mergers within the context of astrophysics, cosmology, and fundamental physics. And so this is really exemplified by what happened in the 2 seconds following the actual merger. So what I'm going to play here in the bottom panel will be that you'll see essentially the time frequency chirp signal, this ever-increasing frequency and amplitude from the gravitational wave merger. And you'll actually hear it. And then 1.7 seconds later, the Fermi and integral satellites actually observed a burst of short gamma ray bursts. Now, within those first 2 seconds and these observations, we were able to actually measure and constrain the speed of gravity, or that gravity actually travels at the speed of light, to 1 part in 10 to the 15 for the first time. From the gravitational wave strain itself, we were able to infer the neutron star masses, which are shown by these orange bubbles here, and the blue bubbles up there show the binary black hole mergers that were observed in the first 2 years of the LIGO-Virgo first 2 science runs. So just to express that we really have this diversity in the fundamental properties that we still have yet to understand with black holes and neutron stars. From the gravitational wave strain and essentially triangulating the arrival times of the signals at the 2 LIGO interferometers as well as at the Virgo detector, which just happened to come online 17 days before, we were able to actually pinpoint the host galaxy to NGC 4993 in the Hydra cluster. And this was done at 11 hours by a whole suite of optical telescopes in Chile. And indeed, the continued monitoring of the ultraviolet, optical, and infrared light, as well as looking at monitoring the spectral evolution of the event over a period of several weeks, really pinpointed the fact that we were looking at a transient event unlike any that we'd ever seen before in the universe. And so what this movie is showing, and I think this really is just simply spectacular, is actual data from the Very Large Telescope in Chile, the ESO facility. And you can see, I'll start the movie again, but you'll see this initially blue featureless spectrum that is very typical to the photosphere of a sun, essentially rapidly redden over several days' time scale, and you can see these broad line absorption features, which indeed were indicative of the spectral footprints that were expected from neutron star mergers, where this material actually produces the R-process elements, which are shown in yellow here in the periodic table. So these mergers these optical counterparts of these mergers are often referred to as kilonova, macronova, but indeed I actually prefer the term bling nova because, as you can see from the periodic table, these mergers and this particular event really pointed to the fact that we were able to show that we could produce all the heavy elements such as gold, platinum, and silver within these neutron star mergers. So in some sense, the cosmic mines of heavy elements. coming on to the final discovery, I think, or the main discovery of this event. In astronomy, one of sort of the most basic endeavors that we have are to measure the distances to objects. And this is really so that we can actually map out the expansion history of the universe. And indeed, for this binary neutron star merger, we were able to measure from the gravitational wave strain by measuring the distance to the source, having an absolutely calibrated distance, as well as the host galaxy redshift, we were able to actually measure the Hubble's constant from this one event, which essentially encapsulates information about the energy density of the universe. So I think this was really a spectacular, beautiful result, once again emphasizing the beauty of actually joining gravitational wave and electromagnetic radiation. And I'd just like to really stress that all these multiple discoveries associated with this one event have resulted in multiple breakthrough discoveries that are now impacting many different diverse fields, from astrophysics, cosmology, nuclear physics, as well as general relativity and gravitational physics. And really to stress that this is only coming from one event. Okay, so I'd like to end my talk by talking really about the future and where we're going. So since the 1st of April, the LIGO and Virgo detectors switched online again after being offline for 2 years. And in the last 6 months, we have already sent out alerts to the entire world of more than 20 binary black hole merger candidates, as well as more than 5 neutron star binary merger candidates. So we have really entered this new era of population statistics, and in some sense, gravitational waves detections are becoming routine. Now, I think in the next 6 months or so, the next big discovery will indeed potentially be a neutron star black hole merger that we will hopefully observe in gravitational wave and electromagnetic radiation. Why is such a mixed binary so interesting? Well, compared to just smashing 2 neutron stars together, we'll actually be seeing the effect of having the singularity on any tidally disrupted material from the neutron star, and in some sense that it's a cleaner signal in both gravitational waves and electromagnetic radiation. And of course, the unexpected. Critically, we already have several new facilities operating in the optical as well as the radio and the high energy. For instance, the Zwicky Transient Facility, which is located at Mount Palomar. And in the near future, we will have wide-field optical and radio telescopes, such as the Large Synoptic Survey Telescope in Chile, as well as the Square Kilometre Array in Australia and South Africa. And all these instruments are enabling us to have this multicolored movie, as well as multi-wavelength movie of the dynamic universe. So moving away from just having traditional snapshots of the universe. And by having a dynamic movie, this really makes it prime to actually go after these very short-lived transient events and to actually detect more. In terms of gravitational waves, on the ground, in the next 5 to 10 years, we will see the current instruments actually undergoing significant upgrades, as well as new detectors coming online in Japan and India, so the CAGRA and LIGO India projects. And excitingly, in the 2030s, we will see the next, there are 2 very interesting proposals to build the next generation gravitational wave detectors, the Einstein telescope in Europe, and the Cosmic Explorer, possibly either in the USA or Australia, which will allow us to have a volume reach, which I'll return to, of a factor of 1,000 or greater. In space, in 2034, the European Space Agency and NASA are leading the efforts to launch the Laser Interferometric Space Antenna mission. So essentially here, the aim is to have a constellation of 3 spacecraft separated by 2.5 million kilometers, forming a precision interferometer in order to actually measure gravitational waves, this time in the millihertz regime as opposed to the tens to kilohertz regime that we're seeing currently by the LIGO and Virgo detectors. And so I'll just show the movie again, but sorry. Some nice music, but you can essentially see that you have this triangular constellation that will be trailing the Earth in this heliocentric movie. So in this heliocentric orbit. So really just spectacular in terms of actually measuring supermassive black holes as well as galactic white dwarf binaries. And so coming to really what should we anticipate, and I think for me this is kind of the plot that really, or the schema that really keeps me up at night, as well as I find it tremendously mind-blowing in the 2030s if we do see these ground-based gravitational wave detectors coming online together with LISA. What I'm showing here is essentially in this donut plot, the yellow dots represent binary neutron stars, the white dots represent stellar mass binary black holes such as we've observed, the orange dots supermassive binary black holes of 1 million solar masses. And you can see on the radial coordinate, essentially this is the redshift or the distance, horizon distance away from us. And the blue and the purple and green lines show the horizon distance for the third generation detectors, the Einstein Telescope and Cosmic Explorer, compared to LIGO, and the red line shows the horizon distance for LISA. So essentially, within the frequency bands where we're sensitive to the specific masses, we will be observing all the neutron star and binary black hole mergers that exist in the universe. And we should be prepared, and I think this really is sort of the thing that I find just outstanding, to the prospect of measuring 10,000 neutron star mergers per year, as well as 100,000 binary black hole mergers per year from the ground-based third generation gravitational wave detectors. So I really find that yeah, that really does keep me up at night quite a lot. But of course, if you see, for instance, sorry, because I don't have a pointer, the stars in the middle, essentially the yellow star shows where the binary neutron star that I mentioned, which was discovered in 2017, is located, as well as the white star shows the first binary black hole merger. You can really see the horizon reach. So it's just astounding, but we will not necessarily have the EM facilities to follow up every single event. And so in that spirit, we really are, as a community and as a field, having to think about using these compact object mergers not only as cosmological probes, but also to be able to inform us about something about the large-scale structure and extragalactic astronomy. For instance, how did our own galaxy come to be? So I think this is really where we're facing. We're moving from this discovery era to one of precision physics and being able to answer these fundamental questions. What is the intrinsic nature of black holes and neutron stars? How do black holes and neutron stars drive the evolution of the universe? And of course, using these as test beds to see and measure how fundamental laws of physics interact in strongly field gravity. And just to end with a reminder that we are, as we heard this morning, we are opening the spectrum of gravitational wave astronomy, this several decades in frequency space. I have mainly talked about the high frequency end of the gravitational wave spectrum as well as the millihertz regime, but just to mention that, of course, there are several other experiments that have already started, such as pulsar timing array, that will be observing a much larger supermassive black hole binaries, and that there'll be a plethora of other compact object mergers or events, as well as the unexpected that we hope to observe both in gravitational waves and electromagnetic radiation. So just to conclude, I strongly believe the future is both loud and bright, and it's really wonderful, I think, to see all the young people in this room, because this really is a field that we're watching and experiencing a transformative step happening sort of right now, right, this week, and indeed, alerts are happening, I think as I speak. So really, thank you very much.
Question on your right. Just a small point, but regarding discovery for the production of heavy elements in the cosmos, it was interesting that, well, first of all, element 43, technetium, allegedly only occurs, does not occur naturally. It's it's been produced, but element 61, promethium, was not apparently found. Of course, it's a very rare element on Earth. You think that that's a function of the sensitivity of the assay, or is it just something specific about that element that would have not led to its production?
So I should actually mention that within this one event that we observed, only last week was there a paper that actually claimed the detection of strontium in this particular event, but for all the other elements, we have not necessarily observed the individual spectral lines, because essentially when this neutron-rich material is ejected, it's moving at a third of the speed of light. So essentially the lines that you're seeing are Doppler broadened. So it wasn't possible for this actual event to individually identify the elements. So what you're seeing in this periodic table are actually the predictions that have come from detailed nuclear reactions in order to actually, in terms of the predictions that we expected for these kind of kilonova, but they're not actually the measurements from this one event. The only element that has actually been stated as being measured is strontium, but this is, something that, one wants to do in the future with foreseeable events happening.
Over here. Was the frequency of these events shocking to you or the team in general? And do you think that over the course of time, these events are supposed to be more or less frequent as the universe expands and stuff?
In terms of actually observing the mergers?
Or the occurrences themselves, I don't know.
Yeah, so I think if we look at the mean rates, I think in the universe at the moment, there should be a binary black hole merger happening maybe every few minutes, and a binary neutron star about every 20 seconds, if you sort of extrapolate from the mean rates that the 11 events that I've mentioned have actually have actually given. So, I mean, I think it's quite extraordinary. I personally was, because I have been working in this field since I was an undergraduate, basically, I became increasingly more pessimistic as my career progressed as to when gravitational waves would be detected. So I have to say, in some sense, I was really blown away by the first binary black hole merger. I didn't necessarily expect, given the uncertainty in how we actually understand how binary stars evolve, there was 1,000 orders of magnitude uncertainty in the actual merger rates. So even in the most pessimistic scenario, I think, if we hadn't detected anything by the early 2020s, it would have been interesting for constraining binary stellar evolution. But I have to say that the universe is actually quite generous, I think, definitely from this binary neutron star merger. I mean, having worked in this field, I never expected that the first electromagnetic counterpart, the first gravitational wave merger from a binary neutron star would be seen in every part of the electromagnetic spectrum, and that it would be quite so close. I mean, it had a signal-to-noise ratio. I mean, you could see in the chirp of 32. So it was just incredibly bright, and it really was, in some sense, the golden binary. But what we're seeing already in the last 6 months is that there are very interesting candidates, but they're not necessarily quite so close by, and actually finding the electromagnetic counterpart is non-trivial.